Hello everyone, Georgios Papadopoulos here and welcome back to COMNET Protocols. Today we are looking at an execution example of the Trickle algorithm standardized as RFC 6206. Let's break down how it works in practice and understand why it's so important for efficient information dissemination in networks. Let's consider a simple network composed of 4 nodes: alpha, beta, gamma, and delta, where the dotted lines show the neighboring relationships while the green arrows indicate the routing parent-child relationship. We will also assume that when any node transmits a message, all other nodes in the network hear it instantly, so there are no delays or message losses. In this example, we will use a redundancy constant k equal to 2. And before we go through the example, let's quickly recall how the Trickle algorithm behaves during one interval. Each node begins with a counter C of consistent messages heard initialized to 0. Next, each node independently sets a transmit time t chosen randomly within the interval I over 2 and I. And whenever a node hears a consistent message before its scheduled transmit time t, it increments its counter C by 1. Then when its transmit time t arrives, the node checks whether its current counter C is less than k. If C is less than k, the node transmits. Otherwise, if C is greater than or equal to k, it suppresses its transmission. Here we see the timeline for each node over one interval length of I. At the beginning, the counter C is set to 0 for all nodes in the network. Finally, the legend shows that the red lines represent the control message transmissions, the yellow dotted lines indicate the reception of those messages, and green lines show the suppressed transmissions. Now, let's assume that node alpha transmits its control message first at a transmit time t between I over 2 and I, as mentioned previously. All other nodes in the network receive this message and increase their counter by 1. Next, node gamma transmits its own control message as its counter is equal to 1, which is less than 2, and all the other nodes, alpha, beta, and delta, receive it and increment their counter by 1. When node beta's transmit time arrives, it suppresses its transmission since its counter is equal to 2. And later, node delta will as well suppress its transmission since its counter is equal to 2. When the current interval expires, Trickle doubles the interval length I, and at the beginning of the next doubled interval, Trickle algorithm resets the counter C to 0 and sets again the transmit time t randomly within the interval I over 2 and I for each node. Similar to the previous iteration, the Trickle algorithm will be repeated. And in this case, we can assume that beta transmits its own control message first at a transmit time t between I over 2 and I, and all the other nodes in the network receives this message and increase their counter by 1. Next, node gamma transmits its own control message as its counter is equal to 1, which is less than 2, and all the other nodes alpha, beta, and delta receive it and increment their counters by 1. As a result, when node alpha's transmit time arrives, it suppresses its transmission since its counter is equal to 2. And finally, node delta will as well suppress its transmission since its counter is equal to 2. Let us now proceed to the key takeaways based on this example. In this example, we observed only 2 transmissions per iteration, while our mesh network consists of 4 nodes. As a result, the Trickle algorithm reduces redundant transmissions while guaranteeing that information is effectively propagated across the network. Now, even if we increase the mesh network to n nodes, all within radio range, the expected number of control message transmissions still saturates around k, which is 2 in our example. And that's it for the Trickle algorithm standardized by the IETF as RFC 6206. Thanks for watching, and I will see you in the next COMNET protocols video.